Hello, I'd like to discuss and demonstrate the electromagnetic spectrum. Here I have a scale with frequency increasing from left to right, starting out with a frequency of 10 to the 4th cycles per second, or 10 to the 4th hertz, going from there to 10 to the 6th, which is a million, 10 to the 8th, 100 million, and so on, 10 to the 10th, 10 to the 12th, on up to 10 to the 22nd hertz and beyond. Looking at the various parts of the electromagnetic spectrum, we start with radio waves here on the low frequency end of the spectrum. They would be typically in the kilohertz or megahertz range. And then we have microwaves going from 10 to the 9th to about 10 to the 11th hertz. And then from there up to visible light, we have infrared radiation. And visible light goes from a frequency of about 4 times 10 to the 14 hertz up to about 7.5 times 10 to the 14 hertz. That goes from red light to violet light, and I'll demonstrate that in another movie. And then above visible light, we have ultraviolet light, and then above ultraviolet light, we have X-rays up to about 10 to the 19 hertz, and above 10 to the 19 hertz, we call those gamma rays. So that's basically a quick overview of the electromagnetic spectrum. Notice here that as the frequency increases, the wavelength will decrease. Here we have a relationship between wavelength and speed and frequency, where c here is the speed of light. Speed of light is c, 3 times 10 to the 8th meters per second. And the wavelength is equal to the speed of light divided by the frequency. And of course, that's the speed of light in empty space when we're talking about the speed of light being 3 times 10 to the 8th meters per second. So the frequency and the wavelength are inversely related. So as we increase the frequency, we decrease the wavelength. So as the frequency increases as we move to the right, the wavelength will actually decrease. So next I'd like to demonstrate radio waves. Here I have a transmitter, and this transmitter is going to send electrical oscillations along these antennas here. And the electrons are actually going to oscillate back and forth with a frequency of around 10 to the 8th hertz, or about 100 megahertz. So we have a frequency of around 100 megahertz, about 10 to the 8th hertz, and those electrons, as they oscillate back and forth, will send out electromagnetic waves. Those electromagnetic waves will come out towards me and go out in the other direction. Some will go up, some will go down. And we'll be able to pick up those electromagnetic waves with this receiving antenna. If I have it properly oriented here, the receiving antenna then will pick up those electromagnetic waves, and let's talk about the electric field component of that. The electric field is going to be horizontally, either in this direction or this direction, and when that electric field hits this antenna here, it's going to cause the electrons here to oscillate with the same frequency as is being transmitted. And as those electrons pass back and forth through this light globe, it'll cause the light globe to light up. So let me see if I can turn that on, and then we'll see the light globe light up. And as we turn the lights down, we can see that even better. And notice that the light globe lights up because the receiving antenna is receiving electromagnetic waves from the transmitting antenna. Notice also, if I rotate this 90 degrees, where the electric field vector is horizontal, if I orient it so it is designed to pick up a vertical electric field, it doesn't pick it up, demonstrating that these electromagnetic waves are polarized. So we pick up the radio waves when it's oriented this way, but the signal cuts out in terms of the receiving antenna when I orient it this way. One other thing we can notice, and that is when I bring it closer, the light gets brighter, and when I take it further away, the light gets dimmer, thus demonstrating the existence of radio waves in the megahertz part of the spectrum.